Hi everyone. In this video, we'll be talking about some of the graphic display options for your electronics projects, and in particular, these cheap ones. These are like $1 or $2. These cheap TFT LCD displays from AliExpress and other. Perhaps you can find them over eBay as well. There are a couple of options, but yeah, these are as cheap as they get. And we will also be driving it with a PIC18F series microcontroller here. We'll just talk through the driver and the schematics, and I will also add the code to the driver and the schematics, everything in the video description below. So, you have a great project. Now you just want to add some graphic display to it. I recommend you to choose a graphic display in the early stages of your project. So it makes everything easier when you're designing the power and understanding the power requirements of your project. So you can just put one on later down the track, but it's easier design-wise if you pick an LCD first, pick a display first, and then design the rest of your circuit. It's also quite important that you need some kind of a capable micro for it. Like many micros out there can drive those displays, but you need some pins. In this case, just it's a 4-wire SPI. You need 4 pins, but a little bit more than that if you want to drive like the backlight intensity and all the other stuff. And you will also need some memory to get the fonts in there to do fancy stuff with the graphics. Since you have something so flexible, you just want to use it, why not, right? So yeah, that's also quite important. So if you know what kind of display that you will be using in your project early on, it makes making those decisions easier. So okay, you just need a graphic display like this one, and what do you do now? You have basically three options. So your first option is just to visit one of your good old catalog suppliers and look at the LCD screens or graphic displays for a project. Can look at the size and the price and pick what is the stock available and pick what is right for you, the power requirements. Well, obviously, the good thing about these catalog suppliers is that they're like, these products are from legitimate manufacturers. They have proper data sheets, it's as you would expect. And in these data sheets, you have all the technical features of the display and as well as dimensions. So if you are serious about manufacturing your project, then that's probably your only viable option. Or you can just go and talk with one of the manufacturers, depending on the number of units that you are planning to manufacture. You can secure some supply, and then that's going to be consistent, right? Your another option is to hit one of your maker retailers. Core Electronics is here in Australia, one of my favorite. They're just selling all these, maker premium quality maker products, really. So it is like one such screen from Adafruit that's being sold by Core Electronics. It's from local Australian stock, and it's 41 Australian dollars. So it's very similar to what we will be looking at today. It's 1.8 inch TFT LCD display, even probably the same chipset. But the difference is these products are very, very maker friendly. So if you don't want to spend a lot of time trying to understand why your graphics display doesn't work, or if you're not very comfortable with the SPI and your micro, you can just probably buy an Arduino, buy one of these, download the drivers, and that just does a lot of hand holding, especially if you are new. And it's just, very well documented. Very good support for it, really. Obviously, these are also RoHS compliant, which means these are lead-free products. So if it ends up in the landfill, it's okay. But with these other cheaper displays, they're usually using lead solder, and that's not good for living things, right? Well, same with anything you buy from catalog suppliers. You can just check for RoHS compliance. So that's the same, pretty much same deal. Unfortunately, with these cheaper displays, such as these ones from AliExpress, and there's like a whole bunch of sellers, and there's a whole bunch of different products. These are the sort of things why it's cheap. Like you don't actually know what kind of materials are used in this production, what's the drivers, what are the chips, all that stuff. And also the data is quite limited and sometimes inaccurate. And with these margins, you can't really expect the sellers to put, you know, all sorts of technical details here. You might ask them, some of them might, you know, vaguely answer you in their best effort way, but it's usually you get what you get and you don't get upset situation. So it's not, if you're going to manufacture some, properly manufacture some number of units, this is probably not the way to go unless you contacted the manufacturer in China and then you secured some sort of stock with them. Uh, but other than that, for, you know, prototyping projects, they're completely fine. I used a number of these screens. Some of them had issues, but they all worked to a degree. But one of the problems is that, you know, they all are different, and like there are slight dimensional differences, there are slight differences with driving them. So yeah, it's a bit of a hit and miss there, really. But they work for the price. I think it's fair. Let's have a closer look at one of these screens. For example, these are like two different kinds that I acquired over the years. So they seem to be, well, I bought them to be the same, but they are not. So that's one of the problems with these, right? It's not consistent. So this one is a different size. The frame around it is different. So it's not a big deal for prototyping purposes, but if you're designing a casing for it as well, if you're designing some sort of button, some interface around it, and if you are building like 1,000 of these products, it's going to be a big problem, right? So there is that. The pins are identical. There's a voltage regulator here, which I found to be different models, but they are very, very similar voltage regulators. And bit of a difference in the silk screen here. But aside from that, they seem very identical. However, they are not. I'm just using the same code to drive both of these. This code works well with this one. It does not work well with that one. I don't know why. It could be a problem with my driver, or there's something different with the chipset. It's very hard to tell. They're supposed to be using ST7735S TFT drivers, both of them, but they could be like just knockoffs or just, you know, replicas of these chips, because this one works fine and this one is the same. You see the animation, it works fine with the driver that I'm going to show you. But this one, whenever I push a byte to it that starts with a 0, it just resets, the whole screen goes white. And then when I push another byte, just any data or command byte really, it comes back to its sense and it just starts displaying again. So I don't know, I already spent a couple of days with it. If you know the issue, if you're familiar with it, let me know in the comments. Maybe it's an SPI issue, maybe it's a communication problem. I'm not entirely sure. So, and also like with these ones, there is absolutely no support. You're on your own, you have to figure it out. But usually these problems are not very difficult. You can just, you know, debug it one way or another. But yeah, it's just a bit of a hassle, really. That's what you're paying for, the price. So on the front of it, we obviously have the LCD screen. We have an SD card holder here. This is, it's not doing anything. This is just like a breakout basically for an SD card. And it's also connected to its internal regulator. So if you power this up with 5 volts, these the 3.3 volt regulator will be powering up your SD card as well, which is good. And for the communications with the SD card, all the pins are here. You can just pop in the SD card, hook it up to your microcontroller. You obviously need some sort of file system implementation, and the microcontroller or microcontroller does the whole heavy lifting here, but it's a nice enclosure and a nice breakout for an SD card. Well, aside from that, we have the silk screen here, 1.8-inch TFT. Yeah, this works with SPI. SPI stands for Serial Peripheral Interface. So this is a 4-wire SPI, and it's 128, 160 pixels. That's the count of pixels. This way, 160 pixels, 128 here. So let's talk about the pins a little bit. So we have this, see if I can hold it in focus. Okay, so we have this LED pin, that's for driving the backlight of the LCD screen. You have the SCK, that's the clock for the SPI signals, and STA, that's the input and output for the SPI, so it's just both connected to the same pin. A0 is for data command select. So this thing is 4-wire SPI. That's what it means. Like you need 4 wires to get the SPI communication sorted. Clock and data is the 2 of them. Data command select is the 3rd one. And you also need the chip select, that's the 4th one. So use the chip selector because you can connect as many as you want this to these screens and the SD card, and you can hook up a lot of stuff in the SPI bus, and it just you need to get this chip select low, so you pick a device to use the bus because they can't use the bus at the same time. So that's what it is for. And this data command pin is for when you when you write bytes to it, you have to tell the chipset, the driver inside the module, whether you are writing a command or a data. It needs to know about that. And what else? We have the reset. Obviously, you need to drive it high to keep the device in on mode. You can just hook it up to your microcontroller, or just drive it high with the resistor. That's all good. Talked about the chip select, and you have ground and VCC at the end, which is obviously the power supply. So this thing, I recommend you to use 3.3 volt power supply for this one. It makes everything easier, and the circuit here and the driver has nothing to do with, but the circuit, we will talk about the circuit here, which is using a 3.3 volt power supply, and it makes everything easy. And when you use a 3.3 volt power supply, it's usually a good idea to just solder this jumper here. That shorts the internal 3.3 volt regulator. So if you don't short it, that's not a big deal. Everything will still work. If you short it, it will probably consume less current because now your supply isn't going through the regulator, and the regulator has a bit of a waste current going on there. So you can just avoid that. But it works both ways. It's not that crucial really. So if you use a 5 volt power supply, you can connect it straight to VCC, and the internal low dropout voltage regulator will be supplying the LCD driver on the module and the SD card as well. So that's good, but it's not going to do anything for the pins, right? So if you are supplying your microcontroller with 5 volts, and your microcontroller will be driving these pins as 5 volts, and that might damage the driver inside the LCD module. So you need to use a level shifter on these pins, and that's just a bit of more components, right? So if you just drive everything with 3.3 volts, you don't need that. You don't even need to put any resistors, nothing at all here. It's just going to work. Same with your LED, right? If you are using a 5 volt to drive the LED, you need to pop in a current limiting resistor there too. But if you are using 3.3 volts, there is already an internal resistor on the module, so you can just directly drive it from 3.3 volts. That's not a problem. So yeah, that's pretty much all we have on the back of it and all the pins. And let's have a look at our prototype a little bit, and then we can just jump onto the schematic and the code, etc. Okay, yeah, it's a very simple prototype. So we have here PIC18F45K20. So this is the replacement of 18F4550. I had a whole bunch of them for USB purposes, and microchip recommended replacing it with these ones. Oh, these ones doesn't have any USB modules on it, but it's all right. It's a very powerful advanced range 8-bit microprocessor. And you can use any microprocessor to drive these graphic displays, as long as you have the enough pins for the SPI and enough memory to get some graphics going on there, so, or whatever you need. So yeah, we have this microcontroller. We have some bypass caps for the power, the voltage regulator, and a bit of a crystal stuff going on here, just because I wanted some real-time clock in this one. Not that the processor needs any oscillator, because it has a high frequency internal oscillator with PLL, can go like 64 megahertz without any external crystals. All the others are just connections really. There's just some pin headers here, and just using jumper wires coming to the breadboard, and everything is connected to the pins on the graphic display. No resistors, no nothing at all, straight connected to the microprocessor. And let's talk about schematic to see what I'm talking about. We have the LED that's connected to RD7. I picked RD7 in particular for this pick because it can expose its hardware PWM signal on this one, and I just wanted to adjust the LED brightness as well. If you don't want to use a pin for the LED, you can just use a You can just connect it straight up to 3.3 volts, or if you are sourcing the, if you have 5 volts, you can just connect to 5 volts with the current limiting resistor. It's all fine. The next two are SPI clock and SPI data. The clock is connected to clock pin, SPI clock pin on the PIC. If you are using the hardware SPI module, that's the only option that you have. You can also use software SPI. It's just, but we're not going to get into that. But I would recommend you to use the hardware SPI if you can, if your microcontroller has it, because that will free up a lot of resources, so you can focus on your solution. And the next pin we have is the SDI, that's the SPI data input. So the PIC will have different pins for the this particular PIC, and many other PICs I know, they don't have a common pin. They have like an input and an output pin for the SPI. But our display has a single pin for the data, but it's bi-directional, so you can just read and you can write data to it. We will mostly be writing data to it, but you can also read the device ID and you can read the memory, which I did. It was a bit of an adventure, and let me know if you really have to read the memory of these screens, because you need to turn off the hardware SPI and send a dummy clock and then keep reading, so it's a bit tricky. I'm happy to tell how it's done if you want to know about it. But yeah, basically the input and output pins, they both will be connected to the data pin, so that's fine. And the next one is the data command select. You can just choose any pin for it. I pick RD2, but any output general purpose output digital pin will do. And for reset, well, this pin this pin needs to be connected to our micro, because depending on your writing data or clock, we'll be switching it low and high. And the reset pin, I also connected to a digital RD1, in this case to our micro, but you can also just drive it high with the resistor, with the 10K resistor, just put it to 3.3 volts or 5 volts, that's fine. So you won't be able to hard reset your screen. You might want to do that in certain conditions, but if you don't want it, if you don't need it, and if you need a pin from your micro, yeah, just drive it high. It should be fine. And the next one is chip select. Again, you don't have to connect it if the screen is the only device on your SPI bus. If you have multiple devices on your SPI bus, yeah, you have to definitely connect it to your micro to just pick which device to communicate with. But if you have only one device, you can just drive it low. That's how you do it. And then the display will always be active. So the rest is ground and power connections. As I told before, I'm just powering everything with 3.3 volts, and ground is connected to the ground both. So it's all good there. Okay, now the code is quite simple. I'm not gonna get into the details of it because yeah, this is just a demo code. You can just read it. I'll just be putting the links to the GitHub repository for this code. But let's get into some of the details of the driver. So you can use it. You don't have to do anything aside from setting the pins. So in our MP lab, I'm just going to open the header files, and there's the TFT SD config header. And here's where you just need to do some definitions to tell the driver how do you communicate with SPI and where are those pins connected to. The first definition is SPI write, and then you have to put your SPI write function here. In this case, I have used the code configurator to generate the hardware SPI configuration, and it generates the SPI exchange byte method, and I'm going to show you how the code configurator works in a sec. Reset set high, reset set low functions, again, these are generated by code configurators. We are basically telling the driver how to set the reset pin to high or low, and same with the chip select pin, same with the data command pin. And you also need to occasionally set the SDO as input and output. That's for reading data. I'm not gonna get into the details, but it's just a digital pin. So if you put the appropriate functions there to set it as a digital input and digital output, it should be fine. And the last one is for the LAD. Again, you don't have to provide these. You can just put an op in all these functions, not all of them, but the LAD ones and the reset one and the chip select one if you're already driving them without the microcontroller. But otherwise, just, you're just gonna put those definitions here so the driver is able to work. And the last bit, yeah, let me show you what we have in the, because you don't have to use this PIC18F 45K20 whatever. You can just use any pick that you want. I have driven this with 24s, 32s, 16Fs, but I'm going to show you how to configure the hardware SPI using the code configurator. So we just need to go to the window menu and then MPLab code configurator. Just open it. I guess it's coming up, takes its sweet time. And we are interested in a couple of modules. One of them is the system module. You click on the module name and then you see all the easy setup details. And then if you want to configure, if you can't see what you want to do here, you can just go to registers, and with the help of the data sheet, you can just change some of the flags here too. So on the easy setup I'm just gonna go through the oscillator configuration of our microcontroller because it impacts the speed of the SPI communication as well. That's why. And in this case, I'm using an 8 megahertz internal high frequency oscillator with PLL enabled. So this puts our system clock at 32 megahertz. And this is important because next, let's check our MSSP module, which is responsible for the hardware SPI. And there are some real simple options here. Yeah, we want the serial protocol to be SPI. We want the mode to be master. So this means this device will be generating the clock and picking the chips to communicate on the SPI bus. SPI mode isn't important. These displays work with both 0 and 3. Input data sample at middle is the default value. It will just work. And with the clock source selection, I picked F oscillator, frequency oscillator divided by 4. And the good thing is just it shows you what is the actual frequency based on this selection. So in this case, it's 8 megahertz. And I couldn't get faster than 8 megahertz with this display driver. Maybe using a software SPI you can, but the next available option here is I can just increase the internal clock to 16 megahertz. That will put it at that will put the SPI at 16 megahertz, and you can't communicate with these displays at 16 megahertz. It's just plain too high. And one last thing is the pin module. That's how I configured those pins. Is you don't need to do anything about SDO and SDI. As soon as you enable the MSSP module, they got set as digital outputs and inputs respectively, so that's fine. I needed to set up RD7, RD2, RD0 and 1. These are like not really related to SPI hardware SPI module. So these pins are for the LAD and what were the other ones? Let's have a look. RD1 was the reset pin. Yeah, there it is, connected to the reset pin of the display driver. RD0, I use it as a chip select. RD2 is the data command one, so you just need those wires as well. You can pick any pin that you want. I just deliberately picked those pins because they don't have any special functions, and they're just general purpose IO pins, digital pins. You probably don't want to pick any pin with analog capabilities because then yeah, you will just be losing that capability basically. So yeah, you can just pick any digital pin capabilities of which that you don't care about or it doesn't have, so it's fine. I'll just put the links to this code and the schematic as well to the in the description down below. So feel free to check it out and do whatever you want with it. So there's nothing inherently wrong with these screens. If you want to, some of them might, it's obviously consistency issues. You never know what's going on in there. You are not quite sure, even though like they list the sellers do their best effort documentation there. Just put some chips there. It's usually SD7735S or compatible drivers, but it's hard to tell what they have in there. So but aside from that, they're really the cheapest option available, and there's absolutely nothing wrong with the display quality here. I mean, the camera isn't doing just any justice to it, especially if you stick with your primary colors. Red, green, blues are amazing. The viewing angle, yeah, it has its problems, but so does all other LCDs has their problems. There's nothing particularly wrong with this in the sense of quality from a display point of view. And yeah, let me know if you have any problems, any comments, suggestions. I'm super happy to see those comments. Thanks for watching and see you next time. Bye.